I'd like to welcome you to the final presentations of the results of the workshop 99. We have a relatively rich program, as you see here. We have had 4 teams, 2 of which will talk today, and 2 remaining teams will talk tomorrow. Just in case you want to glance at tomorrow, this is tomorrow's schedule. I don't know if we distributed in the back there are the programs.
As a correction, tomorrow morning's presentation will be from the time interval you stated, but not the content you stated. In case anybody cares.
All right, so, right, what can I do, right? I mean, a director of a workshop is completely powerless. And I am in the hands of those who are going to present things. Anyhow, I just wanted to point out that we have present here eminent experts in all the fields conceivable that have anything to do with our workshop. The eminent experts are listed over there. During the talks, some of the talks today and tomorrow will be designated as proposal talks, and they have to do with the fact that some students might wish to receive financial support to continue the research started here, and these eminent experts are going to judge whether these proposals, whether and to what degree these proposals are worthy of the money to be spent on them. I guess I should say that we will announce the results of this competition at Friday lunch. This is designed so that you come to Friday lunch, and there is also a reception and banquet on Thursday at 7 p.m. to which you are cordially invited. I'd like to just close by pointing out which teams are going to be talking and who the members of these teams are. So in the morning today we'll have presented to us the results of the first group, which, as you see, is toward language independent acoustic modeling. I'm not going to take wind out of their sails, so they will explain themselves. The sentence that's there in boldface should somewhat explain it. The idea is to try to get recognizers that are well trained on one set of languages to somehow cooperate to do speech recognition on another, shall we say, new language, or at least a language that has in our parlance insufficient amount of data for training. And in the afternoon, we will have talks on the normalization of non-standard words, which has to do with how do you pronounce various acronyms, abbreviations, and foreign words when you're given their spelling of the abbreviation, etc. But but you don't. How do you pronounce it? How do you figure out a way to do it automatically? Tomorrow we'll have 2 more teams. One of them has to do with topic detection and tracking, and the particular task at hand is to identify a new topic in a stream of stories, or how to identify new information concerning a topic that's known. And finally, we'll have a talk on statistical machine translation, which is going to concentrate on doing the machine translation statistically, both on a, quote, well-funded language like French, and a language which perhaps does not have as much familiarity. In this particular case, it's going to be Czech. And the idea is to extend the IBM approach and extend it not just so it can be applied to new languages, but so it can be applied quickly. All right, without further ado, I'll give the floor to Wilbur.
So good morning. I'm going to introduce our problem and sort of direct the show this morning. We have quite a lot to cover, so I'm going to try to keep things going at a quick pace. We'd welcome any questions about clarification of points, or to make sure that nobody is listening goes confused. But I request that we keep extended discussions till the end, just because we have a lot of people and not a lot of time. So. Most of the people on this list will be presenting, and I'd like to acknowledge two people who won't be, just so that they get their share. That's John Morgan from West Point and Nino Peteric from the Czech Republic, from Charles University. They're not presenting, not because they didn't contribute substantially to our progress. They actually did. In fact, John was invaluable. He brought Russian data to us, and as well as models. And Nino's general speech recognition expertise and Czech knowledge, Czech language knowledge, was also extremely helpful. So this is our goal. We want to use speech models from diverse source languages to build an ASR system for a target language. And why are we interested in this? It's largely a practical problem that motivates it, although it's interesting for other reasons as well. But statistical ASR systems require expensive resources. So if you want to train a system, you need speech databases, which usually have tens of hours of speech. You have to collect this data. You have to get transcriptions that say what words are in the data. You need pronunciation dictionaries that describe what sounds make up the words in the data. And then you need text collections for language modeling. So these are sort of the three domains within which you need to collect resources, and we focused on the first one, arguably because in some sense it's the hardest to obtain for many languages. And the problem is that for most languages, little or no data is available. There are a few well-studied languages in the world: English, Spanish, Mandarin. But if you run into a language at random, say, the odds are you won't be able to get these databases in the form that you need. And since we have statistical techniques that need data, your ASR performance won't be good on these languages with our no technique. So there's a variety of possible problem scenarios you could formulate to address problems like this. And our goal, what we decided to do, was to borrow from English, Spanish, Mandarin, and Russian and try to improve a small Czech system. So we assume that we have a small amount of seed data in Czech, and we're going to try to borrow from all these other languages to improve that system. Okay. So what's the sort of framework within we're working? How do we compare what we've done to the way things are often or usually done? And multilingual ASR systems usually treat languages independently. So we're not the first people to work on several languages separately. But in general, the techniques usually work by having separate recognizers from each language running in parallel. And you sort of choose, you make your best guess. I mean, so if you're expecting three languages, say Spanish, Czech, and English, they're running in parallel, and the recognizer that you you sort of decide which one you guess your language based on the performance on the best performance of the individual recognizers. So I briefly want to go through the component parts of the system. So let's focus on one of these systems, say the Spanish system. So we have Spanish data, we have the acoustic data that I mentioned, and also language model training data text, say newspaper text, and we build a Spanish language model for that. And that describes the likelihood of word sequences in Spanish. And then the next stage in the model is a Spanish dictionary, and this describes a mapping from word sequences to sequences of symbols that represent sound in the language. And then given this symbolic representation of the sounds, we have acoustic models that provide a mapping from the symbolic representation to the actual data that we're going to encounter in practice. And this is a statistical system. So usually, if you have separate independent systems for each language, each of these components is constructed independently for each language. So what we want to do, basically, is put a big box around everything, and find ways to share both the dictionaries and the acoustic models across languages. So we're going to take the language model as fixed. We're going to assume that someone has given us a Czech language model. And there's two alternative approaches to sharing things across language. Let's see. One is to sort of take the component parts and work with them sort of as individual pieces and figure out how best to put them together. So in this way, you would train systems in individual languages, and then figure out how to combine say the acoustic scores or the dictionaries in the languages. Alternatively, you could take all your data. These are data-driven techniques. Put all the data in a pool, keeping track of what language you came from, and then build models that are intended to represent the data across languages. So these are, in a sense, sort of two competing results, whether you should keep your data separate or whether you should put them together. And one of our goals for the summer was to, in some sense, start to compare what's the right technique, what's the right way to do the data from multiple languages. So we had three themes in our work this summer. So the first thing that we studied was how to merge dictionaries across languages. And we did this because we need to share models and data across languages. The dictionary says, given a symbolic representation, from our point of view, what the dictionary says is, given a symbolic representation of a sound in a language, what model do you use? So in other words, if I have a symbolic representation in one language and I want to borrow a model, I need a dictionary to tell me how to do it. So once we have these dictionaries, they're a way to borrow, to share things across the languages. Okay, so given that we have those things, so this is the sort of first thing that we needed to do. This was not, we actually spent a great deal of time on this, but it was just a necessary step for further processing. So the next thing we studied is adaptation and training of borrowed models. So we have a bit of Czech data, and we're going to attempt to improve it attempt to improve our borrowed models. And then we have the two goals that address this problem. Is it better to keep your data separate and train models in for individual languages, or is it better to pool the data? So in the sort of keeping models separate category, we will attempt to merge models from different ASR systems. And we're going, the technique we've had, that Peter Bayerlein will describe is, that we use for this is discriminative model combination. And an alternative approach to that, well, just sort of a general moniker for describing emerging data to train a single ASR system would be language adaptive training. So if you follow the speech recognition, speaker adaptive training is an idea to sort of normalize out differences across speakers during training. We would like to do the same thing, but with cross languages. So we want to somehow incorporate some sort of cross-language normalization during training the systems. And we're going to measure our progress relative, as I said earlier, relative to Czech ASR systems trained with 1 hour of Czech speech. So this will sort of, in a sense, be the mark at which we're comparing our progress. Anything that beats 1 hour of Czech speech is a success. Okay. I'm going to go briefly over what we have available for our work. We have, as I mentioned from previous work, we have a language model, and Czech is relatively difficult compared to some languages in terms of language modeling. One of the things is there's an OOV rate of about 7% in a 60,000 word vocabulary. We checked this across several databases, several text corpora, and that seems to be fairly constant. So with respect to the speech recognizer performance, if you expect about, say, between 1 and 2 errors per out of vocabulary word, we're working at sort of a ceiling of 90% accuracy or 10% word error rate, if you put it that way. And what we have, so that's our language model. We sort of assume that that's given to us and fixed. We have 2 Czech acoustic training databases that I'll say a bit more about. We had, going into the workshop, or rather early this spring, a red speech database collected in the Czech Republic. And we also, as preparation for the workshop, collected Voice of America broadcasts. We contracted with LDC to do this collection, and then it was transcribed in the Czech Republic. And we have borrowed from, mainly from LDC, the English broadcast news databases, and also, as I mentioned, the red speech corpus, or the Russian red speech corpus from West Point. And we also have pronunciation dictionaries for all the languages. And I won't dwell on the acoustic modeling. I just really, because there's not really enough time, except that everything that we did was relatively standard. And we're using the AT&T finite state machine decoder integrated with HDK acoustic modeling. Sanjeev will say a bit more about that later, but it turns out that using finite state tools to describe the mappings across languages is really a very elegant way to approach this problem. It's quite nice, and the decoder itself is really fast. That's another nice thing. So, okay. How are we going to define our problem? The idea is this. What we wanted to do is start with a good system trained on a lot of data, reduce the amount of data so that the system gets lousy, and then we would borrow data from other languages and try to improve it. So just summarizing, we would train a Czech Voice of America system on 10 hours of Czech Voice of America data. We would test this system on Czech VOA data. And this would give us the performance target. In other words, we would try to get back up to this performance level. Then we would reduce the amount of data, say drop the 10 hours down to an hour. And then from this 1 hour of speech, we would try to build a good or the best Czech VOA system that we could on 1 hour of speech. And then we would borrow and attempt to improve it. And of course, this all made perfect sense, and all the distinguished experts we consulted said, yes, of course, good idea. Wrong. This was really quite a surprise. It turns out that the Czech VOA data is more like itself than anything else. And, well, let me just quickly go through the results. So this is the, say you start with a 13-hour training set, and you build a sort of a vanilla type state clustered triphone system. You get a word error rate of about 27%. So that's more or less what we expected, for instance, given that there's a 10% floor due to OOVs. And there's no adaptation, nothing fancy in here yet. So this is a very reasonable system that we started. We were relatively confident that we were on sound footing. So then the first thing we wanted to try was, could we use monophones? In other words, could we get a decent system that avoided avoided phonetic context? Because this would make the mapping substantially easier. And it turned out that we trained a 20 mixture monophone system. We figured that increasing the number of mixtures would take up for some of the loss due to not modeling context, and that was more or less correct as well on a 10-hour system. So then we figured this would be our sort of good system, and we would reduce the training data and try to make it worse. And we reduced it down to 1 hour of training data, and it didn't get much worse. And we reduced it down to half an hour of data, and it didn't get much worse after that. And we then thought, well, we started trying to figure out what's going on. We ran the decoder on the training set, and it's not much better than running it on the test set. So, and it's extra obvious in there, obviously. But so what we found is that the word error rate is fairly consistent despite large variations in model complexity and training set size. And we did a lot of experiments trying to sort of tease this apart just because it was kind of a vexing problem. And we didn't find any real obvious causes. I mean, I think, you know, you can just say that there's something about VOA, the way these people are talking, that just makes it extremely easy to model and recognize. I put this slide up just to, you know, further sort of confirm that point, and also to describe the test sets that we're using. So, okay, CUCFN is the Charles University Czech Financial News Corpus. This is our red speech data that acronym will be showing up. We have 2 VOA test sets. The first one was a bit smaller. The second one was sort of collected at a later time. The first one was collected at about the same time as the acoustic training data. And as you can see, the accuracy, say, in the middle line there on the 20 mixture monophone model is about, the error rate is around 30%. So we thought one thing, for instance, might be that, well, the tape training and test data, they were collected about the same time. So maybe it's just because of that they're so similar, but not. The second collection is from about a month later. It's not all that much different. We then, sort of out of exasperation, asked our colleagues in the Czech Republic to hook the radio up to the computer and record a couple broadcasts, news broadcasts, and that's this CRO1 database. And we had those transcribed, for which we are very grateful for their sort of volunteer efforts. And it turns out that, of course, yes, this is substantially worse. So the VOA models seem to generalize poorly. In other words, we're actually seeing that the red speech models do better on the across domains than the VOA models do, which is sort of counter to people's experience with broadcast news in other languages. And just one other experiment that Juan Huerta did quickly was to evaluate, to do similar experiments in Spanish to see if this is the nature of VOA across languages. And it does seem to be. There's 2 news broadcasts in the Spanish test set, VOA and ECO, which is a Mexican language news broadcast. And we're seeing this is not a conclusive experiment, but we're seeing similar sorts of behavior. So, okay. In any event, that took up several weeks of our time, and I've got to wrap up here. Let's bring on the next person, but I quickly want to go through the experiment definition. What this meant was that we weren't able to stay within the broadcast news domain because our VOA data was not suitable for use in both training and testing. In other words, whenever we had VOA and testing performance and training, performance on a VOA test set shot up. So we didn't think this was a good was a fair experiment condition. So we actually have something that's slightly more interesting, I think, as a result of that, in that we're going across languages and across domains at the same time. So we'll be, we have our language model fixed, as I said. Our acoustic training data will be 1 hour of red speech. So you can imagine a scenario where if you're interested in a new language, you collect a bunch of speakers and you have them read, and you collect their data. So we actually didn't want to tackle both cross-domain and cross-language at the same time, but we found ourselves forced to. And we have 3 test sets, 2 VOA test sets. You'll see results on both. As I said, you know, VOA is VOA, so you can pretty much consider VOA 1 and VOA 2 to be the same. VOA 2 is slightly bigger. We have the red speech test set, which is harder than the broadcast news test set, and then we have this later collection of non-VOA Czech broadcasts. Okay, so I'm gonna call up Joe Capone in a moment, but I want to say that we made great progress this summer. In fact, we made substantial progress in all areas of our project. We have good cross-lingual phone mapping. So I'll put this up and go through the points at the end. We have found that training and adaptation is extremely helpful. This is, in a sense, just validation of other people's work, but it's nice to see it work. A very novel result, I think, is the DMC combination across languages actually improves. We were able to beat the Czech language system along, which I think is something of the first, at least in our reading of the literature. And we're starting to see some nice results in language adaptive training. We didn't get as far in all our areas as we wanted to, and that's because we sort of got stymied by this test set, and we devoted a lot of time to sorting that out. But, okay, so I've gone over, so I should just shut up and let Joe go.
Oh, that's right. Thanks.
You have to have,
Right.
and you're supposed to have it pointing toward your mouth.
Okay, good morning. My name is Joe Piccone. I'm from Mississippi State University. And I'd like to talk this morning about some of our initial experiments, our baseline systems, where we tried to use linguistic knowledge to build speech recognition systems in Czech or other languages that required no target language training data. Somebody told me that whenever I talk about linguistics in a speech form, I'm supposed to put a picture up of this person shown here, but somehow when I do that, it X's out all the linguistic knowledge in my presentation. I'm not quite sure why, but maybe by the end of the presentation, you can tell me why this is. So let's talk briefly about the goals of this work. We had essentially created this scenario where we had data in English, Spanish, Mandarin, and Russian, and we were going to try to build a Czech recognizer based on this data. We had carefully selected this scenario so that the domains were fairly comparable. We didn't want to get involved in too much channel variations and these kinds of things. So fortunately, we had broadcast news domains in each one of these languages, and we're going to try to recognize Czech. This particular work tends to focus on this problem of trying to recognize Czech without looking at any test data. So we're going to be sort of operating in this area shown in a shaded area here in terms of word error rates. Basically, we're going to try to recognize Czech without doing any kind of adaptation on the Czech data and such. So one of the important goals here is to minimize target language training data. But also another goal, I think, is to try to see somehow if we can build these kind of universal phones or build phone sets that are fairly robust across different languages. So how do we go about this? Well, one of the first things that we did was, oops, did I lose this? One of the first things that we did was to take these recognizers that we had in each one of these languages, and some of these were borrowed, some of these we developed, and we took all these phone sets which were essentially given to us. We didn't really sit down and try to optimize these phone sets for doing multilingual speech recognition. We had these existing systems. We took these phone sets and tried to reduce them into a domain where we could now begin to look at similarities between phones. So we developed a description of these phones based on features and then assembled them into a system where we could easily map from one language to the other. So what does that look like? Well, here's an example of what some of our mappings look like. We had essentially 38 Czech phones, and we went about representing those 38 Czech phones in a variety of English phones, Spanish phones, Mandarin phones, and Russian phones, and mixing and matching as such as appropriate. We have a nice ability based on this to essentially map across the different languages, and we used this kind of a mapping to generate a lot of information like confusion data and such, and try to learn then how to go about combining this information in an intelligent way. So one of the first things to do was to consider a very simple approach where we try to recognize Czech using each one of these source languages, Russian, Spanish, English, Mandarin. We actually started with just Spanish, English, and Mandarin. And when we evaluated these systems, as you can see, we got fairly high error rates on the order of 20% for Spanish and English. Error rates on the order of 80% for Spanish and English. Mandarin was actually a bit worse. We had a 90% error rate for Mandarin. And then we had this Russian red data sitting around that John Morgan provided us with, and it actually turns out that was the last of the languages that we ran, and we find out quite surprisingly that error rates on Russian were a lot lower than the other languages. Russian was giving us error rates on the order of about 65%. And that was interesting because this is Russian red speech recognizing Czech broadcast news. So it's actually, but it turns out Russian, as we've learned, is fairly close to Czech. So one of the first things you learn from this is to, if you want to recognize a new language, find a language that's fairly close to it.
Joe?
Yes?
One quick question. On all your languages, is the sampling or is the bandwidth the same?
Yeah, that's a good point. We adjusted everything to 16 kilohertz sampling. So we didn't try to have models that actually had different sample rates built in. Though I think that, I'm sorry?
You had to upsample some over?
Downsample, I believe, was the only thing we had to do. I think one or two of the corpora came in 20 kilohertz.
Joe, just one more question. On the broadcast news in Czech, what's the distribution across the focus conditions if you were to make that kind of consideration? Is there a substantial difference?
In the VOA, it's pretty much all F0. I mean, there's some discussion and some interviews, but in general, it's all quite well.
Yeah, so I mean, I think we're trying to avoid getting into channel variation type issues and try to focus more on the language issues related to the multilingual recognition. So, of course, when you looked at something like Mandarin, you might say, well, gee, maybe the phone mapping is not quite correct. So we spent some time playing around with phone mappings a bit, and we tried 4 different variants of Mandarin phone mappings. Nothing remarkably different about them, just things we thought they were getting progressively better. But as you can see, the error rates don't fluctuate all that much. In fact, performance seems to be not terribly sensitive to any of these mappings as long as the mappings are reasonable. But we did manage to get a minor improvement with the mapping that we finally thought was fairly reasonable. So the next step then, well, what can we do if we start to mix and match these phonemes? So one of the first things that we did was to try to selectively grab phones from each language based on what we thought was a good match to the language, to the Czech phone that we were trying to recognize. So we built a system where we represented Czech sounds using 29 Spanish phones, 6 English phones, and 3 Mandarin phones. And we got a minor improvement in performance, but again, not a whole lot of mileage out of simply playing with the phone mappings. But nevertheless, a useful baseline. So then we started to do some things a little more sophisticated. The first thing we tried was an approach that involves simply letting every pronunciation of the dictionary be represented as all of the languages, and then let the system choose which language pronunciation it actually liked for the word. We've seen in the literature where this actually has helped a little bit. However, in our particular case, it actually degraded performance a bit below the best system that we currently had at the time, the Spanish system. We actually left Russian out of some of these experiments. One of the reasons for that was the performance on Russian was so good compared to the other systems. We didn't want to sort of unduly bias or influence this. Russian models tend to dominate because they are so much better than the other 3 languages. So we can then take this system and we can improve on it using what we call a multi-phone approach, where we now let each phoneme essentially be represented by any one of the languages, and you can actually recognize the word using a mixture of phones from different languages. And again, we got a very modest improvement in performance from that approach. That was a little disappointing, actually, because we thought this system might do well, and if it had done well, then we could investigate things like how to go about retraining it and such. Now, the interesting thing is that as bad as these error rates are, it turns out that phone recognition performance is actually quite reasonable, and I'll show a little bit more on that in a moment. I apologize for the fonts here. The Czech characters aren't showing up quite properly, but it turns out that even though the overall recognition performance is very bad, if you actually start looking at the alignments and looking at the data at the phonetic level, the phonetic recognition performance is not all that bad. So that was sort of interesting to us because it seemed like the system was actually better than the word error rates were indicating. And with Czech, we weren't quite sure about language model issues and such. So we went ahead then and took all these models and started to look at some confusion data. So we took the training databases in the source languages, and we now went ahead and recognized these with the different phones and tried to generate confusion data to see how different various sounds were across these languages. Was a T in Spanish the same as a T in English, etc. So we generated reference alignments in each one of the languages, and we're able to look at these. We generated confusion matrices involving vowels and consonants and such. And what was interesting about this is that what you find is that these models are in fact very tuned to the languages that they're representing. So here, for example, we have a vowel, and that vowel, when that vowel appears in a pronunciation, it can be represented either as Spanish, English, or Mandarin. But what we see is that when recognizing English data, generally you pick the English model and recognizing Spanish data and such. So there's not that much confusability between the models. The models are very tuned to the source language, and that's probably not the best thing for doing recognition without any training data. And we had actually some plans to try to take this confusion data and to combine it in various ways. But what we decided instead was to do a simple experiment in that regard using an approach known as Rover, which involves taking the outputs of all these different recognizers and then essentially combining them using a voting type scheme. And this was interesting because it also provided us a nice baseline for the DMC system. So we took all the recognizers and essentially combined their outputs at the word level using Rover and got a very small improvement in performance, nothing really outstanding. But we also did this at the phone level, and hoping that if we combine things now at the phone level and then recombine those phone hypotheses into words, we get a boost in performance. It didn't really help us at the word level, but what we found out in doing that our phone recognition is actually pretty decent. Our phone error rates are on the order of 36%, yet our word error rates are much worse than that. And that sort of verified our observation that phone level performance on the system was pretty good. And we haven't really figured out why it is that the word error rate's so low, given a fairly respectable phone error rate. So the last thing that I wanted to mention is, so we now became worried, well, maybe the real problem then with the knowledge-based system is there's some kind of channel mismatch. So we did a simple MLR experiment where we tried to essentially accommodate for any kind of variation in the channel. And that involved training a global transform that essentially attempts to account for the variation in the channel. So each mean in the acoustic models was allowed to be transformed. We used one global transformation across all the models. And very interestingly, that did not give us, it gave us about a 5% improvement in performance. Now, later in our presentations, you'll see that some of the techniques that actually train on check data very quickly get up into error rates on the order of about 60%, whereas we tend to be operating at error rates of about 80% with the Spanish or English models. So this was interesting because it shows that it's not simply the channel. There is some kind of language-dependent change that goes on between English and Czech, for example, and that's really our primary thing limiting our performance. And hence we began to look seriously at ways we could now start training on small amounts of Czech data. So what did we learn from this work? Well, I think one of the things we learned is it's always good to have a language which is close to the language you're trying to recognize. I don't think we've been able to characterize or separate channel variations versus language-dependent issues and such, and that's one of the things we need to do more work on if we're going to be able to recognize data in a target language without requiring any amount of training in the target language. So that's about all I had to say. One other side note, as Bill mentioned, we were able to run quite a lot of experiments this summer. We had a lot of compute power, but every workshop sort of brings its surprises. And this year, because we had all this vast amounts of computing, we actually started to melt down our, among other things. So, but fortunately, my other role at the workshop is data and systems coordinator, and I'm good at that, and I figured out a way to actually make the disk behave itself. Thank you. Fred, yes.
I don't want to comment on or throw some further wood on the fire, but if one took the view that linguistics is worth considering, etc., or phonetics or acoustic phonetics, would these results have relevance? In other words, I mean, I think that results reported at acoustic phonetic conferences have to do with measurements of maybe frequencies or whatever, but not with actual data where the phones have to perform, which is the case in your case, I mean, which is the case here. So do you think that, you know, that we ought to somehow put some claims into the linguistic community and put them, you know, direct them in a more reasonable direction than they are aiming at?
Well, I guess, I think what concerns
or
us.
would they simply condemn these results as irrelevant and just continue on their merry way, patting each other on the back?
I think the concern that we have is that these acoustic models are so finely tuned to whatever they see in the training data. And I think until we break away from that, we can't really argue that we have any amount of language independent or generic phones.
No, I don't mean that you have them, but I would have thought that, for instance, the fact, you know, the concrete results on how different a Spanish T is from a Czech T, from some other T, should really be of great interest.
Yeah, I think we have,
And
we're
that's
right,
what I'm,
yes,
that's
yes.
what I'm discussing.
I think we actually,
You,
one of
you
the,
don't think so, Jeff?
Can
I
we
didn't
hold
hear
a
anything.
general
Oh,
discussions on the
yeah,
end of
I-
the
I beg your
presentations,
pardon.
or
All right.
otherwise not
Fine,
everyone
fine.
will be able to talk. I don't want to discourage you, but we have left time of about a half hour at the end. Okay, so Juan Herta from CMU is next.
Whose picture was that?
what? Famous linguist, I was told. It's very hard to find that picture, I might add. It turns out the information theory transactions don't publish pictures of authors.
Really?
Yeah.
Okay, is this working now? Okay, okay, so I'm Juan Huerta, and I will be presenting the work we did about mapping phones and sharing acoustic models automatically across languages. So the basic motivation of this was that given that we have a collection of languages in which we have acoustic models that are well trained and well developed, and how can we make the best use we can of these acoustic models to recognize a new language for which the data we have is probably more limited or harder to obtain. And we also wanted to know if these mappings that we derived were gonna produce models that maybe we can combine with the data we have available on the target language as a good starting point to start doing adaptation, or probably as a good starting point for training, or maybe just borrow the data and somewhat mix it with the data we have in the target language. So the idea was to do this automatically, to let the data decide and not take a linguistic perspective, but let the data decide which models are going to represent which phones in the target language. So the approach we took was to derive a set of confusion matrices. And this is the method we came up with. So imagine we have a certain segment of speech in the target language we want to recognize. This language, in this case Czech, has some transcriptions. We have transcriptions for that. Now, if we go and label the data, saying that in the language X, in this case Czech, and for each segment, we put the phone label that the segment corresponds. And then, using the same data, but a new set of acoustic models in a different language, say Spanish, we perform phonetic recognition or all phone recognition. And that's the output of Y, right, of the experiment Y. Now we can see that in time, we have a correspondence between co-occurrences between what happens in X and what happens in Y, the output of experiment X and Y. And if we define a criteria to say of overlapping, if we start counting only overlaps which are larger than a certain percentage of the length of the Czech phone, then we can start counting the occurrences between labels of the experiment X and outcomes of the experiment Y. And we can then construct a matrix in which the entries of these matrices are the counts of the co-occurrences between the phones in the Czech language and the other languages. Now, if we normalize by the counts of this matrix, we can start seeing that what we're going to have is a sort of a joint distribution between the phones or the occurrences in the outcomes of the experiment X and the outcomes of the experiment Y. And so this matrix can start looking more as a probability of joint occurrences. Now, so given a certain phone in the source, in the target language we want to recognize, Czech, and given the matrix of where we counted the occurrences, how can we choose which criteria can we use to select the best mappings, or how can we choose the models of a source language which want to represent a phone in the target language? So we explore different criteria to do this. And one of them is, well, given that we have a Czech label, a Czech phone XI, we want to find the model YJ, which is giving me the largest amount of counts. So in the confusion matrix, in a certain row, we just go all the columns the columns are the models in the different languages, and choose the one with the highest count, okay? Another criteria is, well, but there are maybe some phones that are actually appearing more frequently and are appearing all the, they have a larger number of counts. And so maybe what we want to do there is to normalize by the total number of appearances that model had in the experiment. A third approach that we explored was similar to the approach number 2, but we didn't allow a certain model to represent more than one Czech phone. So an example in this case, when we are looking for a model to represent the phone X1, using the criteria number 2, we would select the phone the model Y1, because it's the one who has the highest ratio between the count in the cell Y1, X1, Y1, and the total number of counts in the column Y1. However, Y2 was really close. We're going to use only X1 because it got the highest ratio. Now, when choosing when looking for a model to represent or model the phone X2, we see that Y1 also has a very high, has the highest ratio. And if we choose Y1 to represent X1 and X2, that might not be good for recognition. I mean, having two Czech models being modeled by the same acoustic model. So one of the variations that we explored was to don't allow repetitions of the models. So we went. So what the algorithm was to go back and select the second best in the row X1. So those are the criteria that we explored for selecting the mappings from the confusion matrix. Once we have the mappings, what we did is to take the Gaussians of the acoustic models and actually just concatenate them and into a big mixture of Gaussians, which was going to include Gaussian models from all the languages. We were weighting the prior weights, the weights of the Gaussians by the number of counts, the normalized number of counts of the confusion matrix. So we were selecting, for example, if to represent a Czech, a certain Czech phone, we had 3 best models coming from 3 different languages. We weighted their counts we considered the counts in their matrices to weight their Gaussians in the final mixture. Another alternative we chose is was the intention of the alternative was to try to reduce the number of Gaussians in the mixtures. So, for example, if we were going to select 3 acoustic models to represent a certain phone, Czech phone, and each of these acoustic models have 20 Gaussians, the final Czech phone would be represented by a total of 60 Gaussians, which are probably too many. So by using only the mixture weight, we selected only the top probably 20 or a certain number that we determined to represent the Czech model. So in this way we were able to find mappings between phones. But sometimes we found that some phones in the target language don't really have a very good match in any other language. Intuitively, they seem to be more like a composition of phones coming from other languages. So what we did is to do the same experiment, but at this time, instead of using phones, we use the states of the phones in the different languages. So specifically, we took each phone on the source language, each HMM, and for each phone, we broke the HMM. Each state was now a new HMM by itself. So for example, the phone A here, state 1, becomes the phone A1, and so on, A2 and A3. And we performed exactly the confusion matrix experiment using states instead of phones. So here are some examples of what we obtained from the confusion matrix experiment. So what we have, the first column here are the states of the Czech phones. And the second and third column are the best matches from the confusion matrix. And the next 2 columns are the second match, and the third column, the other 2 columns are the third best match. So, for example, let's look at the phones in Czech. The A was matched to the English language, the phone AAX, state number 3. The state number 4 in Czech of the same phoneme went to the Spanish A, state number 3. And very quickly, we can quickly see that, for example, there are matches which are very good actually. And for example, the Czech phone B went to the Russian B1, B2, and B3, and the English B3, and so on. And there are, of course, many strange things, like, for example, I don't know, this is Spanish Y going to the diphthong AW in Czech. And, well, of course, yes?
Do you have a, why, even on the left column, your indices go from 2 to 4.
Oh yeah, well that's okay. So the models, the states here are 2, 3, and 4, but when I broke them, I actually labeled them 1, 2, and 3.
So you have to add 1?
Right, you have to add 1. Yeah, because there was a null. Sorry about that. There was a null state in the model definitions at the beginning. Okay. Well, one interesting experiment that we did now is to let the Czech models compete. So what we did was to train models on the same data, unfortunately, that we had in 1 hour, and let them compete with the other languages, mix them with the states of the other languages, and try to do the confusion matrix experiment to see who's going to represent the Czech models. And probably as a result that these models were trained in the same data, the correspondence was exactly that each Czech state matched exactly the state that it wanted to represent. So this gives us the good news that, well, at least it's really it's not that noisy as a procedure. The results we obtained were, briefly, the big idea is that we observed was that mixing states is better than mixing phones. Breaking things before mixing them, it gives you better results. The second observation was eventually that adding languages is a good thing. So as we started adding from English, Spanish, Mandarin, and eventually Russian, our performance was increasing. Unfortunately, it saturates, so we cannot go on adding languages forever. The third is the criteria that I talked about to choose the best matching phones. There are slight differences in the results you obtain, but the best results we obtained was using the second criterion, in which we normalize by the counts of the column. And the final observation is that it's better to find not the best single match for a certain phone or a certain state, but to find a combination, a mixture of the best 3 or the best 2 states. That gives, even though that gives you more Gaussians to work with, eventually that helps you to reduce your error rate. So the baseline, our baseline, we compare these experiments with a Czech monophone system, which had a word error rate of 38%. And here, the first mappings were the ones that were described by Joe, that are manual mappings of the phones, and it doesn't matter how you juggle them, you're gonna essentially have an error rate that is around 70–80%. Now, when you start doing automatic phone mappings, you get error rates that are in the 60s. When you start dealing with states, you get error rates which are in the 70s. In the 70s and 60s, and when you mix everything, states and different languages, then our best error rate for state mappings was 54. So we are still far away from the 38, but we have to consider that these are only mapping states, taking states, and no check data was used to train or to modify these states. These are exactly the models that are used in other languages. So without using any check data, except of course for selecting the mappings, we can get from models, using models from other languages, an error rate of 54%.
Do you have to experiment result for adding Russian or in addition to it?
Yeah, for Russian, after we had all these languages, it didn't change much. This is the case where, for example, we saw that Russian are very good models for Czech by themselves. They are probably better than the rest of the languages. But when you already have a very good pool of states to choose from, the adding Russian doesn't really give us more. So we could have added Russian here, but it's actually would just be misleading.
Well, that's a remarkable result, actually.
Yeah.
Well, then you should stress.
Okay. Okay.
So Juan, you're at your 15 minutes. So
Okay.
you
So.
want to make sure you have time for your proposal.
Oh, okay. All right. So I mentioned this. One thing that I said was that there was no adaptation here. So let me now talk about briefly talk about the follow-up work and what I propose to continue working on. First, two small refinements. That is, all we did was monophone, so include context. Context helps. So start, in some way, work around the deal that phones are not really the same across languages, and include the context somewhat. The second is, and the other is to try to constrain the mappings. So it's unreasonable that an L or a consonant is representing a phone in another language. It happened because of because we were just letting the data just drive it, go and choose the best mapping. But try to do a phonetic constraint. And the third, but the major point is to try to include these phone mappings into a bigger scheme. And the idea is this. The mappings we would like to believe that the mappings are doing a good job representing phones. But actually, we cannot really get rid of the fact that if the acoustic condition in a certain language are similar to the acoustic condition in the target language, these phones already have an advantage. So first, try to remove that advantage. Before doing the mappings, try to bleach or equalize the data. Try to move them to a similar point where they can have now you can do your phonetic competition in a more fair way. And then the second, obtain the mappings, and then to obtain the new models, find some sort of corrections. But this time, because you're working with data that was acoustically normalized, you now have the corrections to be phonetically driven. But later on, Bhaskar is going to talk about the initial experiments we did about finding corrections or linguistic phonetic normalization between phones across languages. That is, after the mapping, find a correction or a correction vector, which is tied across states. So I ran out of time now. So
what would you say further?
well, that's pretty much it. Again, the stress here, the point here is that try to divide the adaptation that we are going to be talking later on during the presentation. Try to divide it with two perspectives. First, acoustic normalization that gets rid of the acoustic differences, and the second is now find the corrections that makes the phone more similar. Okay.
So Sanjeev will now talk about training and adaptation experiments. While he's getting set up, maybe I'll just try to put things in context. So hopefully you're seeing a trend, right? The error rate is going down. We've gone from 80% starting, moving down into the 50s. And we're getting this by incorporating, in a sense, more complexity into the mappings between languages. So now we assume basically that we have techniques that give us good mappings across languages so that we can borrow phones and data. And Sanjeev will talk about initial training given these mappings. In other words, given a mapping that allows you to move a system from, say, English to Czech, what do you then do with it? Do with this system that you've moved now that you have it now in Czech?
You used up my first slide.
Sorry.
No, it's okay. This is how it was meant to be. So this is the mandatory title slide. So in case you're confused by all the names in this group, the one with the red highlight is me, Sanjeev Kuranpur. What I thought is I'll make all the people who help with this work in blue, and that way there could be a second level of credit. Then I found out all the names have to be blue other than mine. So I said, okay, because everybody's done
But they are
something.
black, right?
Yes. So basically there is no blue because all these people contributed to the
Mapping.
So this is the slide that Bill sort of summarized, but let me go over it again. What we've seen so far is, okay, you want to recognize Czech. You need acoustic phonetic models. You have acoustic phonetic models in other languages, English, Mandarin, Spanish, Russian. So what do? You say, okay, use some knowledge of acoustic phonetics, or in Juan's case, a little bit of Czech data to figure out or sort of clone for each Czech phoneme a model. And so in case of what Joe said, you'd say, okay, take the Czech T and model it with the Spanish T. And in case of Juan, you'd say, take the Czech T, break it down into 3 states, model the first 2 states with the Spanish T, and the third state with the Mandarin L or something. So that's what we did. And here's a summary of how things go. For Mandarin, we had about 7.3 hours of speech. We trained up a 20 Gaussian mixture monophone system. This is for the people who particularly care about the speech systems. And it gives you a pretty low accuracy, high word error rate, about 88.7. Okay. And then the English system is not so much better. It's 75% error rate. Spanish is 71, Russian is 60. By the way, this is all on the VOA test set. This is a, like Bill described, this is sort of 3 or 4 shows, actually 5 shows at the end. We also have a red speech corpus. And actually, in case people go back thinking of VOA as broadcast news, let me try and hammer it in. This is red speech. This is red speech by well-trained speakers. So that's why it's actually easier, even though it counts as broadcast news. And it turns out that you can do a lot better than any of these by just training a monophone system on an hour of Czech. So the question we asked ourselves was, okay, as a scientist, this is an interesting problem. You have no Czech data and you want to build models for it. What can you do? But the engineer in me said, hey, wait a minute. You need an hour of Czech data? Pay somebody some money or hold a gun to his head and you'll get it. So basically, like, the question changes. What can you do with an hour of check? Like, so something like, get 60 hours of check data can be tough. You do, like, make sure LDC has the time to do it, and there's data, and there are labelers, and so on. But an hour is not bad. So an hour is realistic to expect, and we've already seen from Juan what to do with an hour, like, for instance, construct these automatic phone mappings. There's another option, and that is to say, well, let's just take a phone mapping, something, for instance, that Joe described, and use that to sort of adjust these acoustic models. So what you've done is you've got a check phone set, and you've chosen, let's say, from English, the acoustic models that you're going to use for those check phonemes. Just adjust those models on this hour of data. And of course, people have studied adaptation for a long time. For those who don't know, MLLR stands for Maximum Likelihood Linear Regression. It's a constrained way of adjusting model parameters, constrained enough that you could actually do it just with a few minutes of speech. In our case, we have an hour. And MAP is another constrained way of, it's actually a Bayesian way of adapting model parameters. Works a little bit better than MLLR when you have lots of data, and so on. And we said we'll do this and then test it on the check speech. And of course, for the reasons that Bill described, we'll test on both the broadcast news and the slightly harder read speech. So what does this do? Here's the results slide. So this column you've already seen. These are the word error rates of the hand mappings. And if you just take those mappings of the acoustic models, rather of the check phonings to acoustic models, and do adaptation on an hour of check data, you can notice there is a significant improvement in the word error rate. There is one column over here which says GMLLR. This is a single MLLR transformation. And if you think what this amounts to is saying all the densities I have in my system, I'm not going to change their means and variances by a fixed transformation which is common to all of them. And the intuition, or at least the popular belief in the community, is that this will normalize out gross differences between channel and other things, between what you're trained on and what you're testing on. Yep?
Clarification, what is the error that you're minimizing on the linear regression?
Oh, it's actually a likelihood-based regression, in the sense that you have, let's say in this case, some check data, and you have acoustic models for it. And then what you try to do is you do a regression of the model means, let's say. And the regression error is not any error per se, but it's actually the likelihood of the training data. And on the Gaussian densities, it comes down to very much looking like a mean squared error, although it's weighted by the variance of the Gaussians and so on. So it's actually a likelihood maximization technique, but it looks a lot like a regression or a least squares technique because of the way the densities work out.
So let me understand this. You take an hour of check speech, you just treat that as sort of one condition, and you estimate your linear regression transformations.
Yes.
That 1 hour of check speech.
Yes. And this is supervised.
Okay, it's supervised. Use the mappings that Juan discussed?
In this case, these are all hand mappings. So for Mandarin, I use Joe's version 4. Actually, it's Richard Sproat's version 4. Is he here? Consider yourself acknowledged. And then the English mappings were done by, I suppose, where's Nino? Nino. Nino did the English mappings. Spanish was a combination of Nino and Juan. Russian, I think, was mostly John Morgan. And the models also, by the way, this is where all these acknowledgements come in. John trained the Russian models, Bill trained the Spanish with Juan's help, and so on and so on. So in any case, it's quite clear from this that the deficiencies in phone mapping, like, you just take the best that a linguist, or in our case, pseudo-linguists give you, and basically run with it. But of course, there is one thing over here, which this middle column, which tells you that from 75 in case of English, you go to only 70% error rate when you do a single global MLR. So the gross differences are not that big. The finer differences are within, like, what you do to each individual phone. And that reduces things, the error a lot more. So this is the conclusion. I think I need to go at double speed. I'll make a very quick digression to tell you something. Again, this is some sort of acknowledgement about how we did all these experiments. So I would like to acknowledge the finite state tools provided by our friends at AT&T. If you have these tools, actually a lot of these experiments become very simple. So the line on top, for instance, is how you'd run a typical English recognizer. You'd construct a language model, call it G, and then write it in terms of a finite state acceptor. you'd have a dictionary which you'd then convert into a finite state transducer. And their composition basically takes you from words with weights in English to English phone strings. And you'd have another transducer which maps them to HMMs. And then you'd run a recognizer on this network which comes out on the left side over here. And you'd do something similar for Czech if you had all the pieces. Of course, if you don't have acoustic models in Czech, all you do is write a little transducer which takes Czech phones to English phones, plug in that unit on the left, and then you have a recognizer for Czech. And then Joe described a lot of experiments where he says, oh, let's say if we allow each phone in Czech to be modeled by HMMs from either English or Spanish or Mandarin, then all you do is in that transducer which says English to Czech, make it English, Spanish, Mandarin to Czech. And all you do is change one box, drop it in there, run the program again, poof, out comes recognition output. All of it bad sometimes, but nonetheless, recognition output. All right. Couldn't we do more with an hour of data? After all, people who do adaptation typically talk about 2, 3, 5 minutes of data sometimes. In fact, this was a big shift for me. Last summer, we were talking about rapid adaptation, and I was working with 30 seconds of adaptation data. And this summer, I have an hour of adaptation data. So we said, okay, we have to be able to do something more. Well, we couldn't beat the Czech monophone systems with other language monophone systems. But on the other hand, that's because if you have an hour of data, you can pretty much estimate decent monophone models. And so we said, okay, but we do have triphone models in the other systems. I bet Czech can't do triphones with an hour. So let's bring in the triphones. So we decided to take the triphone systems from the other languages. In my case, I chose English because it's the one system that I understood the best. And took 10 hours of English data, constructed a triphone model, and then decided I'll adapt this model by using MAP and MLLR and the stuff we just described. And here are the results. So if you just do one pass of MAP, this is followed by some adjustment, gross adjustments of the model using MLLR, then on the Czech VOA test set, you get a 35% error rate, and on the red speech, you get 47% error rate, which is about the same as what you would do with an hour of Czech and building a monophone system. If you do some more re-estimation of the parameters, still constrained in the map way, but do a few more passes, now the performance starts to get better. So we're down to 32% error rate on the VOA, 44 on the Czech, and this is already below the Czech target. And then you go ahead and say, okay, let's, if the 10-hour English system works so well, let's begin the really big heavy guys, the 72-hour broadcast news system, which we had built for something else. This system, it turns out, does a little bit better on the red speech, and it sort of ties with the old system. By the way, the difference is a rounding off thing. It's 6.4 versus 6.8. So at this point we said, okay, we've won, we've beaten the 1-hour Czech system, time to go home. Right? So, but I have this, sometimes I call it a bad habit, sometimes I call it a conscience. Well, it's really, and that's a small font, it's trying to say something there, and the message is that, look, I didn't really work very hard to build the best and the greatest Czech system. After all, I beat a Czech monophone system with another language triphone system. And so the question is, what would a Czech triphone system do? Well, my argument went, oh, you can't really build a triphone system with an hour of data. And then the other part went, what do you think? I mean, who says so? I mean, go ahead and build one. Let's see the proof of the pudding and all that. So I went ahead and did that. And here's the same table. And we have a little bit of a surprise. Even with an hour of Czech data, we can build a pretty decent triphone system, meaning it doesn't fall apart. Remember, with a triphone system, you have hundreds of thousands of parameters in the system, and estimating them on an hour can be quite dangerous. But this is where I said, okay, I'll be my own adversary. I'll try really hard to make the triphone system work well and build it very carefully. And sure enough, it's a good 2-3% better than the monophone system. And if you look at this difference, this one went down from 47 to 36, and this one from about 34 to 30. The reason is the adaptation data, mind you, is from the red speech domain. So if you have an hour of adaptation data from the red speech domain, you get big gains over here, but that data is also very suitable for red speech. So if you build triphones on that, you get much better improvement on the red speech domain. It doesn't port so well to the other domain, but it still improves. So basically, it's not yet time to, it's not yet done. We haven't quite beaten the monophone system, the Czech 1-hour system yet. So the challenge still is beat the Czech 1-hour system. It's just we've shifted our target. Instead of beating the Czech monophone system, now we have a better adversary. We have to beat the Czech triphone system. But don't worry, we haven't called in the Marines yet, and they're coming, and Peter will talk about it, so I'll give it to him in a minute. And don't write off these 35% models. They're not our best English models, but we'll see in a minute what they can do. And by the way, as for conclusions, actually, there are several things in the pipe, which, of course, because of the 6-week workshop, haven't been finished yet. One of the things is that the Russian and the Spanish monophone systems were better than the English monophone systems before adaptation. And then I took the English triphone system and adapted that and went on with it. The reason, of course, is that I knew the English system better than the others. But you could, of course, ask what will the Spanish and the Russian systems do. So that's something which we have started working on. John has actually trained up a Russian triphone system, and we're trying to get that to do the adaptation and work on the Czech. The other thing is that the error pattern, the error characteristics of this English system are actually quite different from that of the 1-hour Czech system. And so John Fiskus is here. Yes. So he'll say, oh, do rover between them. You know, they're very different systems. They'll give you something. And sure enough, that's in the pipeline. And the other thing is, this is all tests on Czech red speech, be it VOA or be it the red speech corpus. And we'd like to take on a more challenging test set as well. And thanks to Lenka and Irena, they actually recorded this show, and I transcribed it here in the workshop. I don't think we've done this before. So that was good, and now we have another test set. So this is in the pipeline. And finally, after all this is done, the next thing to do would be to do something starting with Juan's system, where you start off with phones from different languages as your seed for the Czech models, and then do the adaptation. So you'd have a better starting point and adapt that and see what that gives you. And Juan already talked about doing finding out a best triphone mapping as opposed to a phone mapping before and continuing. So that would be a bootstrap for this after he's finished his triphone mappings. But in any case, the one-line message is adaptation seems to significantly compensate for the deficiencies of this phone mapping. And also, if you see the first chart, what happens is if your starting point is better, then the adaptation makes it even better. So I'm not saying don't try to get a good phone mapping. I'm saying try to get as good a phone mapping as you can and then adapt. Because if you look at, will I be able to find that slide? Yes, success. So if you look at this slide, everything improved after adaptation, the good things improved more. So the idea would be to take Juan's best system and adapt that and try to get a good number out of it. So this is the conclusion. If you have no questions, I'll hand it over to Peter. Yeah. Of the means and mixture weights. So the question was, what did I estimate using MAP? The means and mixture weights of the Gaussian densities. Okay, thank you. Peter.
It's working.
That's a trick. We use it to wake up people.
So the Marines are here, and they arrived just in time. Okay, the work I'm reporting about is about application of discriminative model combination for language-independent acoustic modeling. I will go quickly through the theoretical part. I will give you only a rough overview because I talked about last Wednesday about this about half an hour or quite an hour. I will concentrate on the experiments for the multilingual system combination and especially for multilingual phone class combination. The idea is that you have about 1 hour of Czech training data and to try to combine all the models or systems which we have up to this point. Especially the task now was after knowing Sanji's results, not to beat only the monophone system, the Czech monophone system, but even to beat the Czech triphone system, and we will see whether this is possible. So, a rough overview. What is DMC? Okay, the goal is to have an optimal integration or to arrive at an optimal integration of all given knowledge sources into one pattern recognition system, and it is based on the principle of constructing a maximum entropy distribution with help of the models which you have, and to train the free parameters of this distribution such that you minimize the word error rate on training data. So this approach needs at least, I would say, half an hour or 1 hour of training data. So this is not useful to apply it if you have no training data. The basic approach is that you take your models and you combine your models into a log linear posterior distribution, and then you are using, say, some smooth word error count, and you're taking the gradient of that and you're minimizing then your loss function by this. Okay, so this is the only slide. No, it's not the only, which is containing some formulas. Okay, what are we doing is take our knowledge sources so we have some scores or some models which give us a value for a certain word sequence given an acoustic observation X, and okay, we are combining all these models into one distribution, and using this model combination distribution we build a smooth classifier out of this, which gives us a value close to 1 if the classifier would choose the hypothesis for this current sentence, and which gives us the value close to 0 if the classifier would reject this hypothesis. And we optimize then the free parameters of this distribution with respect to the smooth word error count. Now, what is important is how to choose these knowledge sources, so these characterizing functions of this distribution. And it turned out on another test, on the HUB4 evaluation tests on the English data, that it is useful to combine a variety of acoustic models and of language models into one distribution to arrive at a system which optimally interpolates acoustic, long-span, context-dependent acoustic and language models, and this gives significant improvements on the HUB4 data. So this is one kind of application of discriminative model combination, and the other one, which is especially interesting for our purpose, is to structure the distribution into phone classes. This is done in the following way. Suppose you have you have a segmentation of your current hypotheses into phones. You are summing, if you are summing the scores for each phone, you have to arrive at the score for the whole utterance, and you're now classifying your phones into 3 basic classes. This is vowels, consonants, and silence, and you are adding up the scores for these phone classes, and then you are building a log linear distribution out of these phone class models. And we will see how this is performing. Well, the expectations when I came here.
Is a question.
Yeah?
I don't understand how you estimate the parameters of that model. Do you do it for full log linear, or do you do it for component?
For that model or in general?
Whichever is faster, for this model.
Well, what we are doing is, you have here, the free parameter here are these lambda values. Lambda L for the language model, lambda V for the vowel model, and so on. What you're typically doing is, you're taking, or the simplest way is, take your distribution and adjust these values lambda such that the error rate on the training data will minimize. So the simplest way is just to apply grid search or something like that. But there are some more sophisticated techniques, but I cannot explain them because there's no time for that right now. Does this answer your question, or?
Yeah, so go on.
Yep. Okay. Well, okay, the expectations I had were, well, it was some kind of adventure. I knew that it's working on was the journal and on the Hub4 data, but the question was, will it work for another task, and especially will it work in the multilingual environment? So this wasn't clear up to this point. So for the experiments, I will concentrate on the second setup. Suppose you are given knowledge-based mappings of Spanish, Russian, and English models to Czech models, so you have already heard about this. And you have 1 hour of Czech red speech, or you have the Czech red speech system was trained on 1 hour of data, and we have a 1,000 best list on the Czech VOA2 data, and we apply now DMC on this test set using an head-out method because I didn't have development data available. At least I didn't have had these 1,000 best lists on development data, so I had to use this method to estimate the performance of the method. So this seems to be a reasonable setup for a discriminative model combination. And so the point is, at the system level, we are just interpolating, say, the whole Czech system, the whole Spanish system, the whole Russian system, and the whole English system. So there's no special structuring. We are just putting the systems together. And to give you some insight into the performance of these systems. So the Spanish system has a word error rate of about 70%. The Russian monophone system has a word error rate of about 61%. Then I used this 10-hour English broadcast news triphone system, which was Sanji talking about, which has an error rate of 35.1%. And in addition, for the combination, I used the Czech red speech monophone system. So all systems which were used for the mono combination are marked here with a star. And then we have 2 other systems just to compare the results. So let's have a look what is going on here. The baseline, which I had on the best list, is 34%. Now, just applying DMC to optimize the baseline. This is the first thing what I'm typically doing when applying DMC to optimize the language and the acoustic weight. So you then arrive at 32.7%. Now adding the Russian data gives a slight improvement. We arrive at 32.5%. And you already see that we are better than the original red speech monophone system. Adding Spanish, Spanish gives another improvement. So, and then adding the English triphone system, we see that we arrive at a surprise. We arrive at 29.2%. This is more than I expected with DMC on the system level, and we are already approaching the performance of, or coming close to the performance of the 10-hour system. So the conclusion is Russian helps, Spanish helps, and English helps a lot. And the surprise is basically we have really bad systems. So 70% word error systems or 60% word error system, which still contribute to the performance of the overall system. Okay. Now let's have a look at the phoneme level combination. So the first thing what you can do is to combine the Czech language model with the Czech vowel model, with the Czech consonant model, and with the Czech silence model, just to have a baseline. And then the next point would be to interpolate the phone classes of all the source languages. So we take the vowel models of Czech, Spanish, Russian, and English, the consonants of Czech, Spanish, Russian, and English, and the same for the silence. And well, we see that first of all, we can improve the Czech system standard system, which is at 32.7 to 32.1, using this separation into the different phoneme classes. Now, doing the same for the Russian, Spanish, and Czech system, we see again that we arrive at 31.8%, again an improvement. And doing this now on the best system combination which we have, then we arrive at 28.9%. So this means that the structuring into phoneme class works, and that the interpolation of multilingual phoneme classes helps. So to summarize this result, this means that we are able to improve the original 32.7 system, so after optimization of the language weights, down to an word error rate of 28.9, which is a significant improvement. And by this way, we are able to, where is this? Yeah. You see, with these 28.9, we are able to beat the Czech monophone system and the 1-hour Czech red speech monophone system and the 1-hour Czech red speech triphone system. So this is a really nice result. So to finish my talk, what did we learn? Well, DMC is working in the multilingual environment. This is nice news. And what we found out during the workshop is that the size of the best list is crucial. So I started to work on 100 best lists, and this turned out to be not very well set up for DMC. Then the multilingual interpolation of systems performs better than a monolingual 1-hour system, even if it is optimized using DMC. Well, bad models of remote languages can still contribute to the performance of the overall model combination. This is really nice because this is a nice way to put the efforts of people together. If you can, if everybody can contribute to the system just by providing a model. So this is nice for teamwork. Structuring into phone classes improves the classification, and even the multilingual interpolation of the phoneme classes gives consistent improvement. So this is basically what I had to say. Yeah?
If you did it for the state, I don't know, equivalence classification that Juan was talking
Yeah.
about, would that be too much? In other words, would you have too many parameters, or do you have?
I mean,
would your system still handle it?
There are two approaches to use Juan's method, just to combine this into the overall system, and this is really promising because, I mean, the systems which were combined here were far from the optimal point of the 1-hour Czech red speech system. So, I mean, if you have then a system which is close to 30% and you will combine this again into the distribution, it should become much better. And the second, yeah, the point is, if you are working on 1 hour of training data, you are limited to, say, a few number of parameters. So this is the problem. And if you try to work on a state level, perhaps you can find some way of clustering, which is then close to this vowel, consonant, and silent scheme. So one possibility would be, say, you are taking, if you have a 3-state HMM, you're separating your space again into the vowels, consonant, and not for silence, but for vowel and consonants, the first state, then the second state, and so we arrive at 3 times more parameters. This should work, but if you're really working at the state level, or even if you're working only at the phoneme level, if you're not clustering the phonemes into vowels or consonants, this scheme is not working due to the limited amount of training data.
So you are already finding overtraining of the lambdas? Or?
I'm finding overtraining of the lambdas, yeah. Yeah.
So going from 100 decibels to 1,000,
Yeah.
technique work. Have you thought about trying to apply your technique to the lattice so it's even richer?
This is one of the conclusions I found here at the, at the workshop that it would be nice to reformulate the whole technique to be able to estimate the parameters on lattices, because this is then much easier, because it turned to be out to be difficult to create all these invest lists and so on. You have to save this onto the disk and so on. So it would be much nicer if you could do this on the lattices. That's right, but this will take a little bit of effort. It's okay.
Okay, so we have a few minutes for a general discussion, is that right? I only know that we're shy of the time we were supposed to use before the break. So, okay, so then I'd like to summarize some of the points that were made, just because they went by in rapid succession, and then we'll have two more additional presentations after the break. But we've made substantial progress in all areas of our project. As you've heard, we have...
I want to move from the speaker.
Oh.
This way from it.
Oh, okay.
Yeah, don't be in front of it.
We have cross-lingual phone mappings that make use of small amounts of within language data. We've found that training and adaptation can bring sort of non-native systems close to the performance on a small training set native system, and that the adaptation compensates for the mapping deficiencies. So Peter and Sanjeev both make this point, but I want to stress it. It's not that the mappings aren't significant. In some of the work that you'll be hearing about later, and in our future work, the mappings are probably very important, at least we hope they are, because they describe the best way to share things across data. It just happens that these adaptation and training techniques, they're very violent. I mean, they grab the models and they drag them around, and where you started from really just doesn't matter. We've seen that DMC model merging is extremely effective in combining information from models from various languages. They have the interesting result that the multilingual combination beats the monolingual system, and also interesting that that bad models can still be useful. So some questions came up during so language adaptive training we'll probably say a little bit more about after the next succession of talks, but so I guess if there's any questions, I'd like to open the floor for discussion. I think there was something that started to happen, which I guess is sort of inevitable, and that's what is the role of human knowledge given all these powerful statistical methods that we have, and I think there's a tendency to say, well, the human knowledge is not necessary, or we can get around it. But I think the real method, from the real conclusion from this work, and actually from other work that I've seen in the past, particularly with pronunciation modeling, which is that you have to take your human knowledge and give it to the system in a way that the system gets to decide what aspects of the knowledge it can make use of, and then do the best at recognition, because the models aren't able to capture the fine distinctions that humans can make. And oftentimes, if you expect them to, in other words, if you drive your mappings with the idea that a human will be making use of this knowledge, it's not going to work, because the models are just not that good. So any questions about any of the stuff that we've seen so far? Yes, Paul.
I'd like you to speculate on the following. Let us assume for the moment that Fred is as fluent in Mandarin and Spanish as he is in English and Czech.
Okay.
What do you think would happen if we took Red's speech from Fred in English, Spanish, and Mandarin and tried to synthesize Czech models? That is, it sounds as though the basic message is that realizations of phones in various languages differ much more than the variability across speakers. But if you eliminated that effect completely by having a single speaker for all these languages, do you think that one could do substantially better than, if you had, say, 10 hours of English, 10 hours of Mandarin, and 10 hours of Spanish from Fred, plus an hour of Czech? Do you think you could do much better than 1 hour of Czech, given that all these channel speaker variations have gone away?
No, actually. I think probably a 1 hour system trained on an individual person within that language is going to be very hard to beat. But I could be wrong.
I don't understand. I mean, if you're going to take me as an example, obviously, I have a Czech accent in every one of my languages. So obviously, when I speak English, I'm really speaking Czech. So, so I would think that it would be tremendously powerful.
Yeah, I'm not really sure that what we've done this summer really gets to answer a question, can be used to answer a question like that. I mean, I do think that what this shows is, you know, the more and varied data you have, the better. I mean, we particularly saw that with the Czech VOA data. I mean, sticking to that alone would have been a big problem. I mean, the more and richer, you know, the better you are. And actually, we initially were sort of led into the broadcast news domain, I guess. Partly out of fear of working on conversational speech because the overall error rates are so bad there. But in hindsight, probably, well, not in hindsight, but I think what we'll do next is we'll take everything. You know, I mean, we have all these systems, we have all these data, and we have methods to put them together now. And, you know, hopefully we'll see improvement in a variety of domains. Yes?
How many speakers are sampled in the VOA data?
Boy, I should have brought my earlier slides. There's actually, you know, I'll bring the slides for after the break. I'll run back and get my previous slides. But there's 4 or 5 anchors. And then there's about, this is in the test set, and there's about 8 or 9 other speakers. And male and female. And we don't see a great variability across, well, we see a great deal of variability, but there's not any consistent trends. Males and females are about the same. The worst speaker of the lot is actually one of the anchors. We didn't find any real key as to what was going on in that data.
Is the rate of speech very variable?
Well, we didn't do any measurements, but the Czech listeners in the audience, for when we played it, marveled at how easy it was to understand. Yes, Fred?
I was just going to tell my theory here. Obviously, Voice of America is intended to penetrate enemy territory, and with jamming, etc. So they probably have very well-trained speakers, so that you know, even with jamming, you can hear them. Now that there is no jamming, they still have these old speakers. So they are so terrific. I mean, it would be very interesting to, in fact, confirm, just interesting, I don't know, for speech recognition, to confirm it in other Voice of America broadcasts.
Well, we've started on that with the Spanish, and we'll move on that, but it certainly looks that way.
And then nothing overlap between training and test?
Yes, but only amongst the anchors, and it doesn't seem to make a difference.
So the answer is it's not that the anchors are not going to do that.
Right.
Another considered question is the speaking rate per se is not remarkably faster, but this is just anecdotal. The variation in speaking rate is very low compared to the other, meaning they speak at a very even key. Very steady.
When I asked the question about the distribution across focus conditions, I really wanted to focus on the on the Czech radio broadcast that was recorded tonight and
Oh, yeah.
described. Does that broadcast differ significantly
Yes.
in terms of being other than F0?
Yes. Yeah. Can anybody?
And is that accountable for the difference?
There was some. Okay, so the biggest across within the data, the biggest split was between planned versus spontaneous speech, but it was not that big. In other words, it was like a 5 or 6% difference. I think it was overall just a good bit more harder. In other words,
Is
we.
it telephone channel data?
No. So, Jordan?
I was wondering in VOA, what you're seeing is the editor rather than the speaker.
Very possible.
I don't know.
repetitive or clarity, as well as the speaker. And that's a tremendous constraint in PLA.
It's possible, but we don't see big differences in perplexity, and the OV rate's about the same, and et cetera, et cetera. So that may be so, but it's got to be a subtle thing that we don't see in the sort of obvious places to look. Yes?
Yeah, I have a question that I think gets back to something Fred raised earlier, which is what the utility of all the linguistic input on this is. I don't know these languages and the phone sets for them. How much overlap was there, say, at the IPA level? Did the IPA choose the same phones for these?
Joe should answer that.
Well, I mean, there's a fair amount of overlap. It's hard to quantify that, obviously. But I think most of the phones had good coverage with one or more of the source languages.
That is the standard linguistic analysis would give them the same IPAs.
Yeah, I mean, how detailed you get in your IPA search is an issue as well. I mean, is T in Spanish the same as T in English? I don't know. But generally, the consonants tend to cluster very well. The vowels are all over the place. But then vowels maybe are not all important.
What does that mean, time to break?
I mean, we are past our break.
We're past our break. I apologize, but...
we can move it, I suppose.
Oh, okay. Well, no, we can break now, and then can we shorten the break slightly in case there's discussion after the presentation?
Well, okay. Well, so anyway, maybe we should come back at 11:10.
That'd be good.
Rather than 11:10.